So hi everybody. Um, my name is Fei Pan. I am a research fellow at the University of Michigan. Today we will talk about large vision and language models for civil and natural disaster engineering. So my background is a bit more toward computer science. I did my PhD in computer vision and machine learning, and now I continue work on this field. Um, so, um, so what are the large vision and language models? And you can think of traditional machine learning models more like trained on specific task. So a traditional machine learning model is like a single wrench. You focus on one specific task, and you want the model to perform effectively and robustly. Large vision and language models, they are trained to complete multiple tasks. They are more like multifunctional tools that can work on multiple different tasks. And you can also think of large vision language models like a super powerful artificial neural net that trained on giant amount of data and can work on multiple tasks with very deep understanding of human images, both visual understanding and textual understanding. So today, we will talk about large vision and language models. First, I will talk about classification-oriented tasks. We will have CLIP model and GPT-4 model here. We will also talk about segmentation-oriented tasks, and we will have segmentation, a segment anything model, and the grounding DINO. So before we jump into our presentation, if you have any question, please welcome to send in the chat, or we have a Q&A board. You can post your question on that, and I will have a discussion. Yeah. Okay, so first, let's talk about the classification-oriented task. The first one is CLIP. So CLIP, when we talk about current most influential large vision language models, we can't avoid talking about CLIP. CLIP is a large model developed by OpenAI, and it's trained on a huge amount of data set to connect your text and images. And these text and images as two different modalities. They are the first, they are connected to have a much deeper understanding of our human world. Before we get into technical details of CLIP model, let's first look at how CLIP can help us recognize or classify images. So here I provide some examples images that are classified into different classes by CLIP. The first image from a Food 101 dataset, you see that this photo is classified as a photo of guacamole, a type of food with a probability of 90%. It ranked 1 out of 101 labels. And the other classes, following classes, photo of hummus or tuna or blah, blah. So these have a much lower confidence or score compared with a photo of guacamole. And the second example is CLIP predictions from CLIP models. They're given an image of aircraft or airplane. CLIP models predicted as a photo of airplane instead of bird or bear or car. And of course, CLIP models can make mistakes and conduct wrong predictions. You see the images on the right-hand side. The upper image from ImageNet A shows a photo of lynx in a nature park, but CLIP models classify as a photo of fox squirrel. And the bottom images, you see they are apparently 4 objects, 3 calendars, and 1 ball, but CLIP models classified as a photo of 3 objects. So here are some more results about CLIP models. So you can see that there's a difference between CLIP classification and traditional image classification, as you have studied, or we discussed yesterday presentation by Barbaros. So what are the difference between a clip classification and the traditional one? So one thing you might have observed is that clip model classify each image into a caption or descriptions, like a photo of something, a type of food, a type of pet, something like that. So clip models works in this such a kind of format for classification, and also clip models work on various types of data sets, different objects like sports, food, faces, medical images, and nature scene, etc. So to start with, how does clip make classification, and what is actually clip? So what is clip? CLIP stands for Contrastive Language Image Pre-training. It's a vision and language framework developed by OpenAI in 2021. Ever since then, CLIP has been widely adopted in many tasks in computer vision field. To train a CLIP model, we need a large amount of image and their corresponding captions. As you see on the images, upper image, we call them image and text pairs. Due to privacy or intellectual property, the data sets to train CLIP are not publicly disclosed yet. Though we don't know where this data collect from, but they are likely sourced from websites, social media platforms, books, newspapers, and other data provider by OpenAI. CLIP models is also a very strong zero-shot classifier. So what is contrastive learning and zero-shot classification? We will talk about them in the next few slides. So what is contrastive learning? So contrastive learning is a self-supervised learning technique to train a model by pulling together similar pairs and pushing apart different ones. Let's say we train a classification model to classify two classes, dog and rabbit. It is quite understandable that the feature distance between these two dogs should be closer than the distance of a dog and a rabbit. In contrast to learning, we define anchor as the middle dog image. It's an anchor image. And the positive pair of this anchor is the other dog image. And the negative pair of the anchor is the rabbit image. So contrastive learning involves a first image encoder to extract the features from the three images. We have features from the anchor, the positive, and the negative image, and we compute the distance between the features of the anchor and the positive ones, and the distance between the anchor and the negative ones. So the distance can be a simple Euclidean distance. Now, contrastive learning is to minimize the distance of your anchor and the positive, and maximize the distance of your anchor and the negative images. Zero-shot learning is a very popular machine learning method. It's to let a machine learning model to recognize correctly a class that it has never encountered during training. We also call this unknown classes. So for example, we train a model to recognize 4 different animals: tiger, wolf, raccoon, and leopard. And after the training has been done, the zero-shot learning requires a model to recognize panda, which is never been seen during the training. So we call this unknown classes. In previous slide, we said CLIP model is a strong zero-shot classification or classifier because it has been trained on tons of image and text pairs. Now let's look through how CLIP model is being trained, its training process. So we have a set of image and their corresponding captions. There are tons of image and captions pairs. Clip models include image encoder and the text decoder. The image encoder is constructed by transformers from NLP, natural language processing, and the image encoders could be adopted from either a vision transformer or convolutional neural network as architecture. Given an image, each image and its caption, image and text encoders extract both image and text embeddings. Here, you can kind of understand the embeddings as a type of features. In the same process, the image encoder and text encoder extract embeddings from all the images and captions. And we apply, so here, this T1, T2 until blah, blah to Tn represents this embeddings from your captions. And this I1, I2 to blah, blah to In represents the embeddings of your images. And the next step is to apply contrastive learning loss between the image embeddings and the text embeddings, which is to say that we want to maximize the distance of the embeddings from the same image and text pairs. Like we want to maximize the distance of I1 times T1, and we want to minimize the distance between I1 to all the other different text pairs. And the same process, T1 of text embeddings maximize this distance with all the other image embeddings. So through this contrastive learning loss, we want to maximize their same pairs while minimize the distance of different text image pairs. And during the testing process, we look through how to apply clip models onto zero-shot classification. First of all, we have a set of vocabularies, like you can understand at class names, and we have a testing image, and we compose text prompts with the class names in a format of a photo of something, like a photo of airplane, a photo of car, or a photo of bird. We send this text prompt, we call them text prompts, and we send these prompts into a text encoder, which output a set of text embeddings like T1, T2, T3, same, like until to Tn. And in the meanwhile, given the test image, we also get image embeddings from the image encoder. Then we compute the distance between our image encoder Ti1 with all the other text embeddings, T1, T2, then Tn. And we've tried to find out which one the strongest similarities between your image embedding and text embedding. And we take this text embeddings, text prompt as the output of the classification. So apparently here it's the a photo of dog, which has strongest similarities with your dog photo. And this is the process of zero-shot classification for clip models. So here are some training technical details for your clip models. The first existing dataset are pretty small. So compared with clip dataset, training dataset, existing datasets are relatively small. For example, the visual genomes or MS COCO, they only have like 100,000 images, and YFCC, which they argue they are a really large data set, they only have like 50 million. But clip models is trained on 400 million image and text pairs. This is a giant amount of data. This data set constructed from a variety of public available sources, even though they are not disclosed yet, but they are really, really big. Clip models require very little data augmentations reported by OpenAI, their technical report. traditional machine learning models, when we train on a type of data set, for example, MS COCO, we did a lot of data augmentations like cropping, flipping, Gaussian noise, and blah, blah, blah. But CLIP models, since they have a giant amount of data, they don't require a very much augmentation from data augmentation techniques. They only apply, as they reported, a random square crop of the image. And since they do similarity calculation using softmax logits, they also involve a temperature parameters, which is a scalar value. And this temperature parameter is learned automatically without manually defined. And also the text encoders, as we said, is adopted from transformer from natural language processing research. And the image encoder is either they take both convolutional neural nets and the vision transformer. And CLIP models also involves prompt engineering. So one question you might ask, why is using text prompts like a photo of something, a photo of a dog, a photo of a cat, instead of giving a class name or vocabulary to CLIP models? So OpenAI report also did some experiments, and the experiment shows that using this text prompt would increase the performance by 1.3% on average on over 65 different data sets. And for domain-specific tasks or data sets, for example, Oxford pets data set, we can have slightly more specific prompts like a photo of a dog, a type of pet. And also, in terms of prompts, we can do ensemble of different prompts, which can help us deliver better performance. For example, let's say you want to recognize cat images, trying an ensemble of a photo of a big cat and a photo of a small cat would help you deliver better recognition score. So this figure is to show that a prompt engineering and ensemble improve the zero-shot performance. So here we have a table, a figure. The x-axis represents the model complexities. With higher values represents more complex models, which apparently here are resonant. And y-axis here are the average score, the recognition score classification. Compare with the baseline. Baseline models are the contextless class names. Like instead of giving a photo of something, we just give a name, a class name. For example, just give a name cat or dog. But prompt engineering ensemble using in CLIP models, they use a photo of cat or photo of dog. And compare with this baseline using this contextless class names, prompt engineering ensembles here, you see it's obvious that performance was improved about like 5 points on average over different complexity of different models. And the improvement is similar to if we have the same performance using a prompt engineering ensemble, we can have approximately 4 times efficacies of deep learning models. So in other words, prompt engineering ensemble obtains extra performance compared with textless class names. That's why we use these prompts in CLIP model classification. CLIP models also show competitive performance with the 4 supervised methods because supervised methods are predominant methods in many different computer vision tasks. We want to see how the performance gap between the CLIP models and fully supervised methods. Here we have over more than 27 data sets, different data sets. And this is a comparison between clip models and linear props on ResNet 50. This is fully supervised methods. And ResNet 50s, we pre-train on ImageNet dataset. And here we test the zero-shot performance of clip models and their ResNet 50s on different datasets. You can see that the green color datasets represents the models, the performance gain from clip models against the ResNet 50s. And there are some datasets that clip models not working very well compared with ResNet 50 supervised train, like RealRoset or Kitty distance. So those datasets using fully supervised methods are better than clip models. And like Country 211 or Stanford Cars, these models, clip models outperform supervised model by a large margin. And clip models is much more robust to distribution shift than supervised methods pre-trained on ImageNet. So this is a very interesting figure I would like to share. We have here on the left figure, we have 6 different data sets. ImageNet, which is very well known by all of you here. And we have ImageNet v2, which basically a modified version of ImageNet. And we have ImageNet R, which are more different from distribution shifted from ImageNet. They have like different color of bananas. And we have ObjectNet, which are more distribution shifted from ImageNet. So I would say basically ImageNet and ImageNet v2, they are kind of similar, but ImageNet and all the other like ImageNet R, ObjectNet, and even the Sketch and ImageNet A, those images, those data sets, they are, even though they are all bananas, they are data distribution of these bananas are quite different from the ImageNet, original ImageNet. And we have two methods, our zero-shot clip models and ImageNet pre-trained ResNet 101 model. So here we can see that your clip models actually perform. Let me see the spotlight. Oops. Wait a moment. Yeah. So your clip models on ImageNet and on ImageNet on clip models and ResNet, they perform kind of similar performance. But when we test ResNet 101 on quite the other data sets, for example, ImageNet Sketch, which are quite different from original ImageNet, there is a giant performance drop from 76 to 25% of the accuracy. So you see that ResNet 101 pre-train works pretty well or stable on ImageNet, but if it's tested on a different distribution shift dataset, which is a Sketch dataset here, the performance dropped dramatically, which means the ResNet 101 is not very stable on this dataset. And zero-shot clip models like perform very robust and compare with ResNet 101 model. And which is to say that clip models is much more robust in distribution shift than the supervised pre-trained model. Here on the figures on the right-hand side, we see there are different models and their performances are so here's the ideal case that your model trained on ImageNet, if it's on domain shifted dataset, ideally it should perform same performance. But we see that the standard supervised models, they all have the biases or they suffer from distribution shift. But clip models, which is the purple color lines, shows that these clip models are much more robust compared with the supervised models on net distribution shifted dataset. So here, the next chapter, we talk about GPT-4. So OpenAI released GPT-4 in 2023, which became very strong and powerful AI tools to understand and communicate with human beings. And it supports multimodalities like audio, video, images, text, compared with GPT-3 only support text understanding. What is special about GPT-4 compared with 3 is that it has a strong visual and image understanding. The user provides this photo and asks the question to GPT-4, what would happen if the strings were cut? And GPT-4 gives the answer, the balance would fly away. It means that GPT-4 already have a strong semantic and contextual understanding of this photo and have a powerful reasoning capabilities to provide answers like this. And compared with GPT-3, GPT-4 has a much larger model size. And GPT-4 also outperform previous 3 version on multiple exams and tests such as AP Calculus BC, GRE Quantitative, and GRE Verbal, SAT, and Uniform Bar exams, etc. And GPT-4 can also understand, let's see this photo, for example. So can you tell me what is funny about this photo? So GPT-4 actually understands this photo correctly. So this is the answer from GPT-4 tested by OpenAI, saying that the image shows a package of lightning cables here, but actually it's a VGA connector plugged into the phone. And GPT-4 also recognizes different panels of image. And for example, if panel 1 and panel 2, the pack for lightning cables adapter with a picture of VGA connectors. So it's actually understand the humor in this image, which comes from a much deeper textual and visual understanding of GPT-4. And another example, what is unusual about this photo? We said this to GPT-4, and GPT-4 will help us answer that unusual things about this image is a man in ironing clothes on ironing board attached to the taxis. So it has such a strong visual understanding of the photos, even for the unusual behaviors from the human being. And regarding the civil engineering, which most of you might come from your background, I showed example here. This is from my testing of GPT-4. I have a satellite photo showing a roof shape of a building, and I asked the question to GPT-4: can you tell me which roof type of this house among only 3 categories: hip, gable, and flat? And help me explain the reason why. And surprisingly, GPT-4 gives me the answer, not only in terms of classification label flat roof, it also helps us to give me a reason why it detect or answer the flat roof with the following characteristics and also some other explanations and reasoning. So it's a very interesting toolbox to use for multiple different visual understanding tasks. Now let's talk about segmentation task. So segmentation task here, in contrast to classification task, we will introduce two large vision language models. Now, first one is SAM, and also we will have grounding DINO. Segment anything model is a oh, sorry, here I just saw the question. Oops. Wait, sorry. Can't find my slide. So I saw these questions on the Q&A board. Maybe we can discuss after these materials. I think maybe other people, we can discuss together multiple questions if we have. Okay. So, oops. Will you be able to see my screen? Okay, so here, so segment anything models are developed by Meta AI. It has a very strong segmentation capabilities for many natural images and in multiple situations like human activities, driving, city life, and etc. And this is the photo collected from traffic road. You see that segment anything models can segment multiple tasks, multiple objects and buildings and roof. And segment anything model, or SAM, also works on this top-down view images, such as those from sensing data, like the roofs and trees and road, etc. And so what is segment anything model? So here we have a very high level on descriptions of this model. We have, so segment anything model basically is a promptable segmentation. So you have an image and the user provide a set of different types of segmentation prompts. We can provide the points or bounding boxes or some patches or some text descriptions like cat with black ears. And given this different, you don't need to provide all these types of prompts. Maybe one type it would be enough. So the model will take the input from the image and the segmentation prompt, will output give you the mask of the cat with the corresponding prompt. For example, the cat with black ears will give you the mask like here, the cat on the right side. So this is segment anything model supporting different prompts. And inside the model architecture, we will have an image and go through the image encoders and prompt with prompt encoders. And after extracting, the encoders will extract the embeddings from your image and prompts and send into lightweight mask decoders. And this mask decoder will output the segmentation mask for corresponding prompt request. And SAM model is trained in a loop with different types of data involved with human annotations. So we have a model. First, we predict a bunch of initial mask predictions, and we send it into the data pipelines. And then the data pipelines were involved with different human annotations and modification. And we train the model again. We send this data to train the model again. This is the training loop involved to provide more accurate data, thus improve the model performance to detect or segment more accurate segmentation mask. And so SAM is trained on a giant amount of data set. This data set is trained on a giant amount of data set. This data set is called SA1B. It contains 11 million different images with 1 billion masks. And on average, we have 100 masks for each image. So those masks were fully annotated and verified by human. And it has a very high quality and diversity. And to be more specific, this is an overview of segment anything model. So first, SAM is composed of a very heavyweight image encoder that takes the input image and output image embeddings. And then we also have the corresponding mask for this image, go through a set of convolutional layers, and then we have different types of prompts. Probably we have either points or boxes or text, and these prompts go through prompt encoders, and this prompt encoders gets the embeddings for the prompts and takes into mask decoders. So the mask decoders kind of combine the image embeddings and the prompt embeddings to the final mask decoders. And the mask decoders to output different a set of masks for ambiguity. Sometimes the prompts, if you give the point, it might means that there's several ambiguity of the mask that can correspond to this point. So SAM can output multiple valid masks and associated confidence score for this prompts. Here are some architecture details. First, encoders are adopted from pre-trained VIT network, and it supports prompt encoders with different categories like sparse prompts or dense prompts. And for sparse prompts like boxes, points, they are embedded using positional embeddings, and text prompts use the clip models, clip text encoders, and decoders for math image embeddings and prompt embeddings. And we also introduced that it can output different masks for a single prompt. And the loss function to train SAM model consists of a focal loss and a dice loss. Here we have some visualization of SAM zero-shot segmentation on different data sets. And SAM is also a very good, strong single point segmenter. So what is single point segmenter? We have let's say an image, and if we have instead of giving pixel-wise labels, we provide points for the image, and we want to train a segmentation model that can segment our objects like the train and person. So this is a research direction in the field of weakly supervised semantic segmentation. So compare with the state-of-the-art RITM, which is SOTA model for single point segmentation. We can see that compared with the spaceline model, SAM has a very strong performance on different types of data sets, has extra performance gain compared with the previous single point segmenter. And SAM is also a zero-shot edge detector. And so here are some images from BSD dataset, and we can see that SAM can detect the edges of the objects, and it could detect much more detailed edges of the objects compared even with the ground truth. So here you see that the bottom image contains a building with multiple windows. but ground truth doesn't show the edges for the windows. Apparently, SAM can detect all the window edges. The second visual language model for segmentation is called grounding DINO. Grounding DINO is a pre-trained model for open set object detection. So what is open set object detection? So first of all, let's see the traditional standard object detection we call closed set detection. So we have a set of predefined or a fixed set of classes. We train our detection model on these classes. But sometimes if we try to add new classes, the process is very expensive. Probably we're going to retrain the detection model, and it's also very time consuming. Open set detection is more toward a detecting objects of any classes without the necessity to reconsider to retrain, without a necessity to consider adding new classes to retrain the model. So we want to detect not just the bench, but also all the other objects like lion or the ears of the lion and the woodcut. So how to extend closed set detectors to open set detectors? State-of-the-art researchers on open set detectors are is to involve language as guidance. So we have a text encoders here, and the blue boxes here show the closed set detector without language guidance, and the yellow the green box here are the green square here is the text encoders. We send the text to the text encoders, and this will help us get the embeddings or text features. And we get these text features to the bottom closed set detectors. The closed set detectors typically has three important modules. You have a backbone for feature extraction, a neck for feature enhancement, and a head for region refinement. A closed set detector can utilize the language guidance from the text encoders with feature vision and contrastive loss to learn to classify the novel objects or categories in a language-aware semantic space. And this is a bit more complicated. It's about the framework of grounding DINO. I'll just quickly go through the diagram of how it's the network architecture. So first we have a set of input images and the corresponding captions, and we send these images to image embeddings and text encoders to get the text embeddings. And through the feature enhancement, we get updated text features and image features. And we also have a language guide query selection to select cross text, image text features that are sensitive to your text prompts. And and after we get cross-modality queries of the image features, we send it into the decoder to get a model segmentation. The detecting bounding box or image patches, and we have contrastive learning at the very top to maximize the distance of the same classes, same text image pairs, and minimize different image text pairs. And through this this process, we have two modules, submodules like the feature enhancement layers and decoder layers. Considering the time limit, I will skip the technical details and directly go through the results. So from this slide, so grounding DINO is a very strong open set detectors with strong text understanding. So compare with standard object detections, as we mentioned before, it can support multiple objects, novel categories, even classes that has never been seen before. Users can also give some text and phrases as description to specific objects, like the left line. We can detect only the line on the left side, and if you give some descriptions like the bottom man with his heads up, this refers to the guy on here shouting at the celebration of the World Cup. And grounding DINO can be used to combine with stable diffusion models for image editing as well. And people have tried to combine grounding DINO with STEM models for both segmentation and the detection with prompts driven based method. If let's say we have images here given a bunch of prompts like the blanket, lamp, carpenter, couch, dogs, we want to detect and segment all these objects in the image. And this is the image we tried on SEM Center project for building attribute extractions. So we have a input image here, given a set of prompts like facade, roof, windows. Grounding DINO help us to detect different objects, and we have the SAM model. For each bounding boxes, we can you ask SAM to segment the object for us. So we have combining with the grounded SAM combined with grounding DINO, and the SAM help us to both do the object detection and the segmentation. So here are some more results using grounded SAM to do segmentation, detection and segmentation on the categories of trees, road, terrain, windows, door, facade, and roof. So you can see that SAM works pretty well on these exemplary images. And we have also tested some of the interest of yours, which are related to civil and natural hazard engineering. We test, for example, we found some images of the blue tarp. These images, houses probably suffer from the natural disasters, and they put the tarp to protect their roof. And apparently, grounded SAM did pretty well on detecting this the locations of this the tarp area for the roof. And also, SAM can help us for detecting, segmenting the fire damaged houses. You see, we try different prompts: fire damaged house, or charred house, or burnout buildings. Grounded SAM did pretty well for the segmentation of the houses. We also tried some collapsed houses, which these buildings suffer from either maybe earthquakes or other natural hazard disasters. Grounded SAM did pretty well for segmenting the collapsed houses. These are the segmentation results using different prompts, either collapsed house or ruined buildings or wrecked buildings. We also can use grounded SAM for power line and power pole detection and segmentations. And since power line are very small objects, I would say, so it's not very easy to be segmented out using grounded SAM. So you see those areas with red colors, they're not very accurate in terms of segmenting the power line. But for the power pole, grounded SAM did pretty well. Yeah, here are some more results using different prompts for detecting power lines and power pole. Yeah, that's my presentation today. So I would go through these questions, Q&A questions. Wait a moment. So the first question raised by Rachel, why does clip perform better than resonant on some dataset and not on the others? What qualities of the dataset indicate it's better suited for clip models than the traditional supervised models? This is a very interesting question. Let me show you the slide. So I would say, so in this slide, there are some data sets, I would say clip models perform pretty well according to my experiences on those data sets that are less domain specific, like those objects are from common nature life, for example, the cipher 10 like digits or the cars and like cat, dogs. Those images are pretty common in our lives, and clip models can perform pretty well compared with supervised model. This is because clip models was trained on large scale data sets that are sourced from internet. So the objects that are popular in our common life, probably they are also very popular or common on the internet world, on the Twitters or other websites. So clip models pre-trained on these types of data sets, they has pretty well zero-shot segmentations. But for domain-specific data set, like for example, satellite or remote sensing data, those data are relatively less on the internet. So clip models does not give, we don't fit enough types of data to clip models. Therefore, clip models does not perform well on those domain-specific data set compared with supervised baseline. Does it make sense? Okay, yeah. So do you have any questions or any comments? So if not, maybe we can go to implementation part. So here I prepared a set of implementation on Google Colab. I should try to share my screen. Oh, is SAM available on SAM Center? So we actually merged. We actually have functions or module for SAM model and grounded SAM, and we will share on our new release BRAILS++. I think Barbaros is gonna to give a point on that. Yeah. Okay. That's so our next part is some Colab implementations. I want to give you a real interactive implementations of using clip models and SAM models for classification and detection. So So first of all, so we have this code. We will share it on the website so you can download and freely use it. So first of all, we have our clip models for zero-shot classification. Let's first try to. Oh, I cannot connect to the GPU. Oops. Okay. So there are some issues.
Hey, it occasionally happens. And if you have another Google account, it might be fastest to just try that.
Sure. Let me try to connect. Yeah, I think I'll try to use my different Google account. I think free version of Google Colab has some limitations.
Yeah, unfortunately, sometimes it kicks you out of the GPU allocations, which is what Fei is running into. The trick is, at least for me, I have multiple Google accounts, so I just basically switch over.
Yeah.
Like I mentioned yesterday, design safe tools are a little bit more dependable. It's just there's a bit of an upfront wait. Yeah, but multiple Google accounts kind of help.
Yeah. Yeah. All right. I will go to my the other account. So are you able to watch my screen? I think shared. Okay. So here, after we connect to GPUs, we first kind of need to set up the environment. Like we need to install some additional packages and also the packages of clip models from OpenAI. Click on running. So this process will help you download a bunch of packages and install it on your environment. Yeah, I think it's kind of downloading. Before it's completed, we can kind of go through the following lines of the code. So the second block is about set up the NumPy and Torch, and we can check the Torch version. And the next block is to import clip models. So if we set up clip models, we can check the available models in clip model. These are like, you can print it out, basically the ResNet. These are the ResNet 101 and the 50s, and we also have a bunch of models, VITs. So remember, these models are the image encoders. For the text encoders, we have transformers. Okay, the environment is set up, so we can import NumPy and Torch. Okay, it succeed. So here we have the Torch version 2.3 and CUDA as well. And then we can import clip model here. Okay, so we have a set of different image encoders. The more heavyweight the image encoders, I would say it has stronger classification capabilities. So let's try one type of image encoder. Here we will use VIT, Vision Transformer B32, with this VIT model, and then we have we can load this model first, and then we move these models and all the weights into our GPUs. And here are some image resolution, information, and context length, and vocabulary size. You can check how many model parameters. Okay, so for VIT B32, this base version of VIT has a model with parameters of this much, and image resolution, give you the context length and vocabulary size. So vocabulary size are related to your prompt embedding, the size of the embeddings. And for clip models, we also require a pre-process of our image. So in other words, if you have a set of images, you just can't send images as input to clip models. You do need a pre-process of your image. So the pre-process involves a first normalization of your data, and change to the data type of tensor, support PyTorch, and you do some cropping and resize to the standard size of a clip model. Let's run it. Okay, it's pretty fast. And then next step is text pre-processing, and clip models have image embeddings plus text embeddings. So now we're processing on text embeddings. Let's try to see how clip models tokenize hello world. Okay, so given hello world, clip models kind of pre-process it to a set of to a vector, basically a vector, so or a tensor. So you can kind of understand that our texts are transformed into a vector or a tensor that can be pre-processed with image features that is another type of tensors. So if we do not convert to the tensors, the images and text, they're from different modalities. They can't be pre-processed together. And how to process it? This process is going through the positional encodings. It's a very important concept for transformer and other deep learnings. So if you're interested, go through to check it out. And the next step is to set up input images and text. So we first have a bunch of packages, and I would say the very important part would be the descriptions. We have a description from a dictionary in Python dictionaries, each with different keys and the descriptions corresponding to the key. So basically, you will see that this is the name of the photo, and this is the caption of the corresponding photos. Let's first run it. And we will also have a set of photos here. I already uploaded my photo to Google Drive. Now I try to import the photos. This eight images from my Google Drive. to import to Google Colab. Okay, so now my Google Drive is mounted here. You can see this is my drive. And the next step, I will do image loading and visualization. Oops. So I have no content. Let me see. Oh, I think my images are on my previous Google account. So let's see how can so I will try to modify this this line of the code. Just wait a moment. Now I need to upload the images to my Google Drive.
Hey, Fei,
Yeah.
this is great so far. Sorry to interrupt. Can you maybe share your notebook with the attendants? If you go top right, share.
Oh yeah.
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 And then I think I guess like you just go, anyone with the link. Yep.
Sure.
And then
Yeah.
if you could drop it in the chat just so that they can follow along a little bit better. This we like I mentioned yesterday, we make all of the material available on the website, but it looks like we missed this one. So hopefully, until we get it up, you can just follow along with the link that Fei just posted. Thank you, Fei. Sorry to interrupt.
No problem. And also, I will share this Colab on the website Barbaros was mentioning yesterday with the documents and the code links. Yeah, so this is, I just shared the link to the chat rooms and you feel free to click it on. Yeah, so sorry for these complexities. I need to upload the photos. Yeah. Clip classification. File upload. Need to get my files, I think. Okay, so I think we are kind of, yeah, so we are kind of set up now. Let's just try to run. My Google Drive. Says no file. Sorry. Complexities. Yeah, I think it's running. Yeah, so you can see that their setup images are loaded. This is page are the image names, and there was description, a page for text about segmentations. And now we kind of build the features. These are the image input and text tokens, and we embedded them into image and text embeddings. And then we send into the encoders and get the features. And then we calculate the cosine similarities here. These are the calculation process. Now you see that for the cosine similarities, the image here and its captions. So this color, so these are digits represents the cosine similarities. In other words, if it's closer to 1, it means those two modalities, the image and the text, are showing the strong similarities in terms of their features. So so this is basic clip model classification process. We calculate their cosine similarities, and we pick up the most the closest distance, which is for the first image would apparently to be the first text description. The second image, which is astronaut, which is gonna be the second image description. Yeah. So yeah, and I'll just run a few more examples to show zero-shot image classification. So let's first import a diff class names from Cipher100. We have so these are the different image the classes names from Cipher100, and we kind of add the text descriptions in the format of this is a photo of something something. So you have a set of there's 100 different classes, and then we want to kind of classify the 8 images into one of these 100 classes, and we see how clip models can help us do the classification. Okay, so these are the classification made by clip model. So the first image, it's a page with boards, and the clip models will try to get among 100 classes. I think the highest prediction score is keyboard, but apparently this is not keyboard. So, which is to show that clip models sometimes could make mistakes. And this image on the right side, it's astronaut with American flag. Clip models predicted as a woman among 100 classes. I think these are the top 5 classes out of 100 classes. So the top 1 class would be woman, be the final predictions from clip models. Yeah, and also here, this image showing the cat. I'm kind of surprised clip models made a mistake, kind of predict as a sweet peppers, but actually it's very easy to recognize and predict as a cat. And I think the top 2, the second top prediction from clip models is tiger, boys, mouse, and girls. I think sweet peppers are, to my surprise, I don't know why clip models predict as a sweet pepper. Yeah, so this is an example to show how clip models can help us make zero-shot classifications, and hopefully these codes are useful to your problem if you have any classification and want to try clip model. And next one, I will show a ground descent for segmentation task. Just wait a moment. Sorry, I need to log into my previous account. So this is gonna be my second example. I will share the link to the chat room if you're interested. You can enter. I also need to upload my photo for testing. Okay, so this second example implementation is from grounded SAM. So we test using grounded SAM for our segmentation task. As we introduced in the previous slide, it's a combination of grounding DINO and the SAM model for detection and segmentation. So first we will install these packages. It has a lot of packages and it takes pretty long time. I test about for 5 minutes. So we will first run this installation process. Since it takes pretty long time, we can, before it's completed, let's go through the code. And first we will import the models, especially grounding DINO and segment anything model. And then these models, after they are imported, we can detect the GPU device, and we want to load the model parameters for grounding DINO. This is the function for loading the model weights, and this part is for downloading the grounding DINO model weights. They have a lot of models here, and we load the model to grounding DINO. And then for SAM, we also download the model weight and also load it to the SAM model. And after the model are set up, the next step is to make an inference using grounding DINO and SAM. This function is to download a test image from the website. we have this image, very cute peppy dogs, and then we download this image onto our Colab, and we want to use grounding DINO to detect and help us to detect and segment our object. This is the detection function with the input of the image and text prompts and models. And then these models are grounding DINO. And these are the threshold values for boxes and text. And we do, after we detect this prediction functions give us this box and predicted boxes, logics, and then we can we annotate these boxes and logics to our original image, and then we can display this image in this following slide. You can see this image with the detected bounding boxes printed on top of this image. And for SAM, since previous grounding DINO only detect the bounding boxes of the bench here, we want to use SAM to segment this bench out of this bounding box. So this is a segmentation function, which is used to take the image and the SAM model and the bounding boxes, and it will give you the mask output. And the second function is to visualize or draw this mask on top of the image. So so if you have these two functions predefined, we can visualize this photo with the previous bounding boxes and also the mask of the bench detected, segmented by SAM model. And I will also have my own testing image from my Colab, my Google Drive, and this is the here I want to load the image from my Google Drive. We're gonna be this image, and then let's do some detections using grounded SAM, grounding DINO, and also we can using SAM model to segment the detected bounding boxes. So here we can segment, not only detect, but also segment our window. So let's see whether this, this process takes a pretty long time. So we kind of have to wait until it's completed. I think it's almost done. Yeah, we might need to wait for extra 1 or 2 minutes. Yeah, I think it's done for installation. Now let's test. Yeah, I think it's done. Okay, let's import a bunch of grounding DINO and segmenting model. So if you go to your folder, this previous step will download a bunch of packages, grounding DINO. Here, grounding SAM basically contains grounding DINO and SAM model and yeah, a bunch of functions down here. So let's try to load our model to GPU. All GPU is available here. We can download the model weight now. Okay, this step is pretty fast. Let's download the SAM model weight. Oh, some people share in the chat rooms saying that the links are kind of blocked. So I modified general access to anyone who with the links. If you have this trouble, could you please try it again? I think it's better. Maybe I can share the link again. Yeah, please try this newly shared link. Okay. So SAM model weight is downloaded, and let's try to load the image from the internet. So we have this image with dog and bench, and running DINO for detection. Let's detect given the text prompt bench, and we want to detect the bench. Yeah, so you can see the bench is detected. We can also like modify the text prompt to like either dog, maybe dog. Try. Yeah, it help us detect the dog, but I would say it's not perfect. Like grounding DINO, I think it would be better. I would be more satisfied if it detect the whole body of the dog. Apparently, only detect the head of the dog. Let's change it back to bench. Yes, so we have bench here. SAM model for segmentation. Yeah, let's run the code. Yeah, kind of give us the segmentation benchmark, and let's try to load from my Google Drive the photos. I think I would give the access. Yeah. So my Google Drive will be mounted at this location. And now I will import the images from my Google Drive. You can have your own images upload. You can upload to your own Google Drive and modify the code accordingly. So this is the photo of a street view house. We can see there are two houses here, have some windows and doors and the roof. It's a perfect demo for detection and segmentation. Let's do the detection segmentation detection first on window. We give the text prompt window, and then let's ask grounding DINO to detect the window. Okay, so here we can see the windows. Most of the windows are detected. We can change to maybe door, detect the doors. So the door detection gave us one detection of the door, but I would say the other door. This probably is another door. Is not detected out. I think this one seems like another door. But anyways, grounding DINO only detect one door. Maybe we can change to roof. Yeah, it helps us to detect the roof of the two houses. Maybe you can change to tree. We can detect the surrounding trees near the house. Yeah, so here you see the trees are also detected. Maybe can detect the what is it, the facade. Yeah, so yeah, we can successfully detect the houses. Now let's do segmentation of the houses using SAM model. So you see using SAM model for segmentation, and here we visualize only one mask. So that's why only this house mask is visualized. And we can change to one. Maybe we will segment the other houses. This is a very simple code to visualize. If you want, we can visualize all the houses segmented out by SAM model if we change the code. Yeah, sorry. Yeah, so this house, second house also segmented out. So I would say this is some simple demos for grounded SAM and click models. This code will be publicly available, and you feel free to use it. Yeah, I think that's pretty much about my part today. Do you have any questions or feedbacks? Okay, so I will stop sharing and give the stage to Barbaros.
Now, for the rest of today's session, we're going to be doing a hands-on exercise. We're going to essentially pick up from where Fei left on the discussion with grounded SAM, and we're going to basically create a segmentation model for facade parsing. And by that, what I mean is break the building images into individual building components, such as the building facade, the roof, windows, and doors. So we're going to start with creating a model for that purpose, and then we're going to see how we can tap into some of these vision language models that Fei talked about to maybe improve that model. And this is going to be purely hands-on. So we're going to start with a Colab notebook, blank slate, and we're going to sort of populate the Colab notebook as we go. And at the end, we'll create a notebook that will still be visible to you. So we'll still share it on the website. But it will be good for you to sort of code with me, just so that you also have a sense of what I'm doing. You can add your own flair to the code. The main emphasis will be why we would be what's called distilling from a vision language model, and what are some of the great things about vision language models, and what are some of the downsides, even though Fei talked about getting a hands-on practice on some of these aspects will be, I think, helpful. So without further ado, we'll just fire up a Colab notebook and we'll get going. So what I will do now is I will share my screen with hopefully a Colab account that will work for me with a GPU allocation. So give me just a moment here. Colab. And I will share my screen. There we go. All right. All right, so a blank screen, and I will call this grounded SAM, let's call facade segmentation. And I'll call it with grounded SAM. Still. Okay. All right. So the first thing I'm going to do is I'm going to, like I did yesterday, I'm going to start with installing BRAILS++. And for that, we have a somewhat lengthier syntax here. The link you need to basically know to be able to do that. And I will just post that in the chat for everyone to use. You will notice I've placed an exclamation in front of the pip. In case you're not familiar, pip is basically the Python installation, one of the Python package installation utilities. And a lot of the things you will install on Python, you would typically use pip install. Unless you use a Conda environment and for Anaconda, you would typically use pip install. You can still use pip install with Anaconda. You know, there's reasons why you would do that or you wouldn't do that, but I don't want to get into that too much. The main thing here, and I put it in the chat, is the link here. And the git plus in front of the syntax is basically, the link is basically telling pip install to go to the BRAILS++ GitHub repo and install from there. So we're just going to hit run, and this is going to, oops, I need to make sure I have the right runtime first, because we don't want to go all the way to find out that we haven't started this on a GPU. So what I will do is I will change this to a T4 GPU, which will kill this. If I went too fast, here it is. So you go change runtime and then select a GPU option. The options you have might look different. I think this has to do with me being a very long time user of Colab, and they just provided a perk like this. I just have more options than a typical account. But the one you're going to be going for is the GPU option. And I think the one that will be available too will be T4. Okay, so I'm going to hit pip install again, and we're going to let that run. The next thing I'm going to do is I'm going to create a cell here. And I'll post another link in the chat. This is basically the images we're going to use for training. You know, we don't want you to sort of load your own Google Drive or manually upload them. You can just use the syntax that I'm going to be posting here. And I'll be putting basically the entire link here. This will be basically what we're going to be, the link we're going to use to get the data. If you're doing it on your own computer, you can just click on that and hit download. That will be fine. We're doing it programmatically here, mainly because you know, Colab doesn't have even though it has an interface where you can upload things manually. On the left, you see the folder icon, and then it allows you to do an upload here. I'm going to do it programmatically here, just because it's a little bit easier for me at least. But what you can do is you can actually go to that link, download the zip file, and then manually upload it using the sidebar folder icon here, and then upload to session storage here. Okay, so basically, you know, I just copied and pasted the whole syntax here. This is the URL, and I'm basically assigning a variable number for it, so variable name for it. And what I will do is for this one, because it comes from Google, it needs to be downloaded through a package called gdown for Google Download. So I'll import that package. And what I will do is then I will go ahead and type gdown download, this has nothing to do with BRAILS. This is just a utility for downloading things on Google Colab. And then the only thing we're going to do here is now we're going to call this variable. And let's see what else we would do here. We'll put an output name. We probably don't need anything. And I will just hit run. And let's see what comes out. The good thing is now that I have this sidebar visible, you're going to be able to see what's getting downloaded there. So right now, the only thing that's there is the sample data. And what it just did is it actually downloaded this file named building segmentation.zip. Takes, I think, a few seconds for this to upload or update. Let me see. Yep. Oh, I got into the depths of it. There we go. There's the file. Right. What I want to do next is I want to unzip this file. So I will go ahead and put an exclamation. I'm running a command, a terminal command. And I will basically ask, I will basically unzip this file. So it will be BLDG segmentation.zip. And then you'll see that Colab has this auto complete that will basically help you get that portion done too. So and I'll hit that, and you see now it actually created a folder named BLDG SEG, and then it has a bunch of subfolders for the training and validation data. This data I will show you in a second is basically consists of, actually we can probably click through the images here once this uploads. It basically includes about 100 images of buildings and the corresponding segmentation mask for them. Let's see if I can put the user here. Let's see. Click something that I wasn't supposed to. There we go. And then it'll be home, I believe. Nope, not home. Not home. What would it be? Date. Nope. Let's take a look at what the content would be though. Right. Okay, there we go. Content. So I'll double click into that. I guess I can just stick with this too, and then I can hit building segmentation. And what you will see here is once this is unzipped, it will unfold the structure that you need to basically create a segmentation model. What you see is a folder named building segmentation. That's basically what the data was zipped as. And underneath is two individual folders, one named train, the other one valid. You will recognize the structure from the image classification model that we trained yesterday. It's almost exactly the same. The main difference is the subfolders, one for images and the other one for the mask corresponding to them. The masks won't be as easily visible. I will show you later in the demo how to sort of make them better, I guess, viewable. Right now, they're basically just an integer array, basically, an image that only has values of 0, 1, 2, 3, and 4. And those are the classes we're going to train for. 0 would be the background, 1 would be the building facade, 2 is the roof, 3 will be the windows, and the class 4 will be the 5. 1, 2, 3, 4, 5. The last class will be the door. I'll show you a few of these images just to see what they look like. Takes a few seconds to load. There are no restrictions on the sizes of these images. You can really segment anything, with the models that we're going to create. The only thing that's important is for your mask to be the same size as the images. Okay. So this is what it looks like. These are what I call in the wild images. So there's ideal situations where you just have clear views of the buildings, and then there's situations where there's multiple obstructions. These tend to be a little bit more challenging for segmentation problems, and hence a little bit more fun to basically work with, because you can see where the model fails and where it doesn't. And this would be a perfectly ideal case where you have a nice snap around the building, everything's sort of clear and so forth. And the masks, I can open them. You won't be really seeing anything in there. It's just a PNG file, but say there's a mathematical representation of the masks. I will show that BRAILS has a utility that converts these into viewable masks, meaning the image is in there and then it's overlaid with the corresponding masks. We'll do that in a little bit, probably closer to the end of this demo. But for now, this is just some of the images that we're going to be looking at. Okay, so I'm just going to close this. And the next thing we're going to now do is we're going to basically get to training a segmentation model. And you've seen that doing yesterday, I've highly emphasized that one of the missions of BRAILS is to sort of make it easy for the natural hazards community to use these kinds of image recognition tools. And we've done an image classification model training yesterday. So the objective today will be to basically create a building segmentation model. And what you will see is one specific application, but the syntax applies to everything. You don't need to really change anything that we're going to do today to train for a different application. The only thing that's important is for you to have the data set. And I'll, as we go, emphasize on how we can get these data sets a little bit better. And by the end of it, I think it's going to be crystal clear. But if you're curious, this data set is a fairly, this is actually one of our initial data sets for parsing the facades of buildings. And it actually took many, many hours to create these images of just a few hundred buildings, right? And then, you just sort of found a little bit more creative ways to do it, sped up the process. But the traditional way of creating segmentation data sets is a very lengthy process. So once we train this model, the initial segmentation model, I will show you how you can tap into the vision language models to create these data sets a little bit faster, a little bit more convenient. Okay. Okay, so Google's yelling at me for not using the GPU, which means it might drop me off. So we're gonna basically get to it, right? So the first thing I'm gonna do is I'm gonna basically import the BRAILS importer like I did yesterday. So we're gonna go from BRAILS, and this BRAILS package was installed using the pip install in the first cell. We're gonna get let's see, we're gonna get the utilities. And then we're gonna, from that, import importer. Okay. This is just basically BRAILS++ uses a method of abstraction where things could be called using this generic importer method. It basically enables you to pull all the individual folders of BRAILS without really needing to change your syntax. So then the next thing we're going to do is, now that we have the importer, the syntax for the importer, the command for the importer in, is we're going to now call the image segmenter. And to do that, you're gonna see a syntax very similar to what we used yesterday. So I'm gonna call the importer by initializing its class construct. And then the next thing I'm gonna do is I'm gonna call this maybe my segmenter, and I'm gonna import my segmenter. So I'm gonna go ahead and enter importer get class. This is to get one of the classes of BRAILS in, and the right one will be the image segmenter. Very similar to what we used for classification, right? The syntax was image classification for creating a classification model. Okay. So far so good. Is everyone able to follow along okay? Any questions? Feel free to unmute or use the chat for this. Okay, don't see anything, so I think we're good. The next thing I'm going to do is now I'm going to actually create an image segmenter class, and that's going to be from my segmenter. Let's see. this, and then I will go my and then I will just put parentheses there. Okay. All right. Now we just need to now that our segmenter is basically created, the only thing we're going to need to do is to define a few parameters for our training. The main ones will be the data path for the images. So I'll call that data path. And then you can see that right now we're in the content folder, so it will be simply PLD, let's see, PLD SEG, right? So that would be my data path. And the next thing we need to now do is basically enter the syntax for training. So for that, we're going to just go image segmenter dot train. And there's really just a few things we need to enter here. The directory for the data path, where the training data is. Data path. We need to define the classes we're going to train this for, the segmentation model for. And for that, I need to probably define a variable. I'll call that, what will I call it? Segmentation classes. And then the last thing is I'm going to enter the number of epochs. You don't typically need to do this, keep similar to the classifier model. This syntax will allow you to train your model for a very long time by default. And if it detects that the training is not improving, like it was the case for the building for the image classification module, it will basically kick out of the training and give you the model that yields the best validation accuracy. So normally you don't need to enter the number of epochs. You really just need to enter the training data directory and the classes you're going to train this model for. Here we're defining a small number of epochs because we don't want this training to run for a very long time and take up the entire time of the demo, right? So one last thing I want to do is I defined a variable that actually is not defined yet, the segmentation classes. And for this one, I'm going to be entering a list, and that list will go something like facade. Let's do roof, windows, where's window, and door. And Pep8 requires us to put spaces here. It's really not a requirement, but it just gives you a nice clean code. Let's see, that's everything. I think that's pretty much everything here. Any questions on the syntax? Is that, you can see it's really just a few lines. If I may cheat here, this is just a one command here, right? So you're really looking at, to train a segmentation model, 1, 2, 3, 4, 5, 6, 7 lines of code. And we could have really gotten away with, if you want to be a little bit more compact, just put these in here as arguments. So really the BRAILS syntax is as simple as 5 lines of code. So a 5-liner will get you to a training model. Okay, so let's hit run here and let's get that running. I just want to make sure I got everything correctly. Okay, what it will do is it will default to a model. So we're still performing transfer learning, and you're all familiar with what that is by now. We're still performing transfer learning. Typically, good models to start with, I think, is the DeepLab version 3 that uses the ResNet backbone, a fairly old architecture, fantastic on small data sets. And another one that I would recommend that the image segmenter class has is the UNet model. Again, a very small one, and a fantastic one, for smaller data sets that we will typically work with. There are a lot of really good transformer-based segmentation architectures. If you want to perform transfer learning on those, and this image segmenter class has a few of them. If you want to, use those are also options. Based on my experience, unless you have a pretty big data set, those are not going to be as good as some of these smaller architectures. So I'm not saying basically DeepLab version 3 is better than the transformer architectures. If the data set size is not a matter of concern, but if you do have a smaller data set, these smaller architectures are just better. And think of your basic statistics knowledge, right? With the basic statistics knowledge tells us that if you have a very big model, you need a lot of data for it. And a lot of these transformer models are very big models. So that's something to bear in mind. What we're going to do is we're barely training this model for the classes that we're interested in, right? We're trying to break up the components of a house, of a building. And to do that, we're basically using 4 classes, custom classes, and then there's a default class that's just the background. So everything else would just go to that default 0 class. So essentially, we're really training for 5 classes in total, just 4 custom classes, right? And as the training progresses, you're going to notice, you're basically seeing things similar to the classifier model. I'm waiting for the first epoch to end just to show you a few details here. But like we did yesterday, all it does is it downloads a model, strips it off of its, the classification head, and it's not quite a classification head with a segmentation model like we've talked about. It basically strips it off, puts a new custom one in, and then trains the model. One thing you're going to notice is we have a couple of pretty familiar, metrics here. Training and validation losses. So we want these to constantly go down as long as the training is working as intended. Another thing you're going to notice is we actually don't have an accuracy metric as straightforward as the classification. With segmentation, these accuracy metrics are a little bit trickier, mainly because they don't really, in the global sense, tell you how well your model is doing. There's not a very nice, nifty sort of metric for that. If during training, what you're looking at is an average metric, and that average metric could be tainted by misclassifications with the background, or misclassifications with the edges of the masks. So it's a little bit trickier. What I would suggest is when you train a segmentation model, really just focus on the losses, and if they're basically constantly decreasing, right? And you will see that we have about, I think we're using if I'm not mistaken, a batch size of 2. So that's why we're running 55 epochs. So it's really just 110 images for training, and then we have about 16 for validation. Okay, this is going to run for roughly another 5 minutes or so. So what I want to do is, I know what to expect from this model once it finishes training. What I want to do is I want to write a simple code to display its output. And one thing that's going to come out is once this is done, like it did with the classification model, it will give you a plot of the losses. Since we're going to be training this for such a short time and the data set is pretty manageable for an architecture like this, we're going to probably see a downward sloping line. Okay. Okay. I don't see where we chose what model to use. Is the segmentation model automatically grounded SAM or something else? Okay. So grounded SAM, we haven't done anything with grounded SAM just yet. What basically what we did here was we've defined multiple options, but we left out the model definition. To define your model, you would go model, would it be, let's see, let me add a thing here. And then you would basically define the name for the model. Okay. I think it was, hold on, I think I'm making a mistake here. Let me look this up really fast. How to do that. Oh yeah. Yeah. So to define the model, you would actually go to your, you wouldn't do it here. You would actually go to the, right here, my segmenter, and then you would define a model architecture. And then there's a bunch of options here. You can look at IM segmenter. The syntax will be IM segmenter, kind of similar to the classification class you will go implemented architectures. And what that will do is it will spit out all the implemented architectures, the ones I mentioned, and you would basically pick one out of those and then stick it in here. Okay. Here we just went with the default. That's why we didn't really define a model architecture here. So good question. I can see why it's confusing. I will answer the second part of your question. What we're doing is we're basically now we have a number of segmentation algorithms that were architectures that we're trying a model with. Grounded SAM is a zero-shot model, and you can retrain it, or to be correct, it's fine-tuning, but that model you wouldn't really do like something like a transfer learning per se, right? So that you would use those models to, it's a zero shot, it will give you data if you need it, and you can fine tune it with additional data. But typically, if you want to do transfer learning sort of thing, you wouldn't use those models. Those models are really big. You need a lot of data to do anything with them. So I'm talking about some of the transformer segmenters. Think of 5 times, 10 times the size of those. So typically, you wouldn't take a zero-shot model to do transfer learning. This is a great question. You would take a simpler architecture, and then you would distill a zero-shot model, such as grounded SAM. Okay. Right now, we're training from scratch, correct? We're training from scratch a model that was initially trained on ImageNet data. Okay. Actually, it could be the Cocoa data set, one of the standard data sets. Okay. It's transfer learning off of a segmentation model that was already trained, but not a zero-shot model. Okay. Does that make sense? Perfect. Okay. And you can kind of see, the training is complete. I straight away look at some of the metrics that are sort of granted, right? Did the accuracies go up? They did, somewhat marginally. I wouldn't really got hung up on this too much, right? Because some of the deficiencies of the metrics. But one thing that's for sure is the losses went down significantly, right? In just 3 epochs, we've seen a decent reduction. And the thing is, I'm focusing on the validation losses, but the training losses also consistently went down. So this is good. This is good news. And then this training could have probably went on for longer. Actually, probably a lot more epochs. Just don't want to spend the time for it. So we're just going to stop it here. Okay. The next thing I'm going to do is I'm going to visualize some of the outcomes of this model. So what I'm going to do is I'm going to use a what's it called? A Jupyter specific command. So matplot library is a very common plotting package, and you can call that through Jupyter using the syntax here. This funky sign that you don't typically see with a lot of the Python code is very Jupyter specific. What I want to do is then I want to now get one of the images in here. So I'm gonna say IM path, and it will be, what did I call my data? Where is my data? Data path. Okay, yeah. Data path. And then I have a / there. Let's see. Nope. So what I will do is I'll do add a / here, and then I would, or maybe let's just be a little bit more elegant. Let's just do, I'm going to pull a few images from the validation data set. So I'm going to go valid images like so. Okay, so this is basically defining the path where the images we will perform inference are. Data path was the baseline directory for where the images, the data we use for training are. And what we want to do is we don't want to go into the training images and show that our model works, because that would be cheating. Image validation, it's a little bit dubious. I've talked about that, right? Because it implicitly affects your training still. But these are the only images we have, so we're just going to stick with it. So this is basically defining the path of the images we're going to get. And what I want to do is I want to get the list of those images into Python. So we would use, I think I need a package import here. So I will use the OS package to basically figure out or get a list of the images that are in IAM path. Okay. And I can just run this right now. It won't really plot anything because I haven't completed the code, but I want to show you. Oh, I don't need generative AI. I can show you that it got the number of images, or the names of images. And I think 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I think should be 16. I see 15 here though. So maybe it was 15, but I think it's 110 for training and then 15 for validation. That's what we used. A very, very small data set. Okay, what I want to do is I want to kind of automate this plotting images. So what I want to do is I first want to use the image segmenter. That's what we called it, I think. And then I'm gonna call the predict method. And what I will now then do is I will predict method for the image segmenter requires 2 arguments, the path for the image that we're going to do inference on. So that will be IAM directory, that's the argument name. And it will be IAM. Let's not be confusing here. I'm just going to call another thing called IAM, and IAM will be basically IAM path plus IAM list. And I will pull a number, a random number. I'll start with image number 2. So I'll go image number 2. Okay. And then basically then this will be just IAM dir is equal to IAM. And then the classes will just be, I think I called them seg classes earlier. Yep. It will be just that. Okay. Let's see what comes in. IAM path is not defined because I made a mistake typing that variable name. IAM list is not defined because I made a mistake typing that name as well. All right, so what it's basically doing is it's in 3 epochs, we trained a model. It's showing us what kind of predictions we get with it. This is one of the validation images. The red mask is for basically the roof. Blue mask is for the facade, and the orange is for windows. It seems like it's actually having it's actually doing pretty great with the first 2 of the classes, and it's still needs some time figuring out how to snap nicely to windows. Okay, and I'll just sort of randomly select a few images here just to show you that I'm not handpicking these images. And you can see we're pretty much seeing the same exact thing here. The windows aren't as clear, but the rest of the stuff is fairly good. And I gotta say these are pretty ideal images, right? The level of obstructions are very limited. Let's do number 0. I'm randomly picking these values. It looks like there is a bit of a struggle with this one. So we don't really care about the ones in the background. So if there's quality issues with those, that could be handled in post-processing. The one in the foreground, you can see a part of the roof is not really captured, but it's still doing a pretty good job. And the window snap could be better, right? Let's see. And I'll do maybe 12, just randomly selecting. Yeah, another pretty good one. And it wasn't supposed to get these garage doors, and it didn't, so that works out. Pretty happy with this. It was just 3 epochs, and then this is what we get. I'll take it, right? It's pretty good. But what if we wanted to maybe improve the performance a little bit? You can obviously train this longer, right? But instead of training it longer, you can also add a little bit more data. That might help a little bit too, right? That might, we know that a lot of times, the bottleneck is the data. So what if you wanted to add more data and you don't want to spend hours sort of doing this manually? Like I said, there's clever ways of now, getting, segmentation data, even manually, labeling it. It's a lot easier than it used to be. There are some computer vision algorithms such as watersheding and so forth that will sort of help you, get these masks. There's even, vision language models that are embedded in some of the labeling tools that will help you do this kind of stuff too. So there's all sorts of now new developments if you're interested in manual labeling of data sets. What I want to do is, since we've talked about vision language models so much, and we showed how powerful they will be, they can be. What I want to do is now I want to show you how you can use a vision language model, grounded SAM, Fei talked about, to generate your own data. And we'll take a look at that data together. You will see some deficiencies with it, some really great aspects of it. So hopefully once we get this running and get our images, we'll be able to have that discussion. What I want to do is now I want to paste another URL in the chat. This is the one we're going to use to get an additional set of images. Remember, the first set of images in BLD SEG folder, these are just an image set that was manually labeled, a very good quality data set, but fairly limited in size. So if we want a model that will generalize well to all regions of the US, we're probably going to have tough luck with this data set, right? So from a practical point of view, to even just to improve the generalization capability of my model, I should probably add more photos, a lot more photos than 100, right? Probably on the order of maybe 10,000, maybe 100,000 images. And just for reference, the grounding DINO model that Fei ran, excellent model, great. Not the grounding DINO, grounded SAM model Fei ran. Excellent model, really good predictions, but the computational aspect, it's a little bit, it takes a little bit of a time, right? So you saw, for a single image, it took a while for it to parse. We're all, at least for, natural hazards domain, we're really all interested in things that are quick results, right? Things that will run fast enough so that we can scale them up to regional level applications, right? So hopefully, you will see some of the benefits of using BRAILS++ for running something like grounded SAM with what we're going to do now. And hopefully you will also see, with BRAILS++, there is a faster implementation of grounded SAM that you can use. But you will also see, with grounded SAM, things will take a little bit long. So you saw that these predictions, they're basically just spontaneous, right? You have the smaller model, you just run a bunch of pass in a bunch of images, and then you get the answers pretty much right away, right? Well, I pulled another one where the windows aren't very captured very well, and then the door is completely messed. So maybe not too happy with this one, right? Okay. So what I want to do is I want to copy and paste another link in the chat. Okay. So what we're going to do is we're going to download basically the images on this URL. And because we already have the G down, all I'm going to do is I'm just going to define this URL. I'll call this additional image URL. I think that, let me see. Okay, yep, that's right. Okay. And then what I'm going to do next is I'm just going to call G down again. this is again just to download things on Colab. It's just a convenient way to do it. And then I will copy and paste this variable name. Okay. And these variables, we'll see where they're gonna go. Let's just run this and see what comes out. Looks like I'm having trouble with this one. Let's see if I got the URL correct. Oh, I see the problem. Yep. Okay, let's try it again. And then I don't really need this, right? So, okay. All right. Now it should download okay. Just 7 megabytes. I think this one is just 50 images, additional 50 images. And it downloaded in this file named additional images.zip. So what I will then do is I will do unzip, similar to what we did earlier, and then just pass in the name of the file. And it created a folder named additional images, and you see here it's just a bunch of street level imagery. Nothing else, no masks, no funny business, just images, right? Okay, so now the next thing I'm going to do now that I have the images, let's call grounded SAM to see how we can tap into its magic, right? To do it is as simple as pretty much the last time. The only thing that's going to be probably the longest or tedious part of this will be calling the packages necessary. And I got to look up my notes here because yeah, okay, here we go. So from what we're going to do is we're going to need 2 separate packages here. The first one is from BRAILS processors, VLM segmenter, VLM for vision language model, and grounded CM utility. So now we're calling grounded CM. So we're probably coming to Fred this once for you. I think this is the part that you were looking for. Okay, so import. And
yeah, it is. Can you clarify what name error you had? I didn't quite catch what you fixed.
Oh, name error up here.
In the last, yeah, there. You said
there. Okay, yeah. Yeah, let me actually put this straight in the chat. I guess you had a difficulty with that one, huh?
Thank
Yeah,
you.
what it was I think I copied and pasted, and when I copied and pasted, I like pasted a bunch of things that weren't supposed to be there. That was just breaking the link. So
Cool.
yeah.
Thank you.
Yeah, absolutely. Yeah. All right. So the next thing will be, okay, I'll slow down just for a second, hoping that you'll be able to catch up here if I went too fast. Okay, we really need just 2 commands here. So one is build models, and the other one is run on one image. I will probably clean this syntax a little bit more. I think like we can really get away with just one command here doing everything. So this might change in the future. If it does, we have examples in the BRAILS++ repo, and the documentation will be up soon too. You'll be able to find the updated syntax. Okay. And then what I'm going to do is, so this is really all you need for grounded SAM. You don't really need anything else to be able to run it. But what I want to do is I also want to visualize the images. And to be able to do that, I need another package. And that's going to come from the utilities, BRAILS utilities. There's one called segmentation utils. Okay, and then I will import. What will I import here? Create overlaid image. You'll see a lot of these methods have pretty clear names. We pay attention to ensuring that's always the case. This last one that I added, it really doesn't have anything to do with the grounded SAM. this is just for visualizations. When the masks come out, I want to basically put those masks through this method to create images that are better viewable. And you'll see what I mean by that. If you remember, I showed the masks earlier, they were just black images, because really the variations are so small, you're really not able to see it. So this basically takes that and makes it, explodes the distinctions between the individual masks. Okay. Now all we need to do is basically call the relevant syntax from BRAILS++. Let me see where I am. Okay, here we go. So the first thing we're going to do is you'll remember from Fei's presentation, grounded SAM essentially is segment anything model, SAM, coupled with grounding DINO. And the reason why it's done that way is SAM is great at segmenting, but it doesn't know the labels for the items that it segments. So we use grounding DINO to figure out the labels for those segments. Essentially what's done is we use grounding DINO to put bounding boxes around objects of interest, and then we pass it into SAM, and SAM knows what the predominant feature is and how it should segment it. But you're looking at two visual language models coupled together. Takes a long time to run, right? So and you'll see the BRAILS++ implementation is a little bit more clever about this, and it actually runs fairly fast, but still not as fast as a segmentation model like the one we trained earlier. Hence, another motivating factor for distilling from these visual language models as opposed to using them as. You'll see the second motivating factor once we actually run this and take a look at the output. Okay, so grounding DINO, let's call it grounding DINO model, and then SAM basically, SAM predictor. And then we're just going to call this build models method. It doesn't really have an argument. It will automatically pull the models we need for running grounded SAM. And the next thing we're going to do is we're going to do, okay, so I'll just enter the, I'll take this method right here. And then I will basically put in the required arguments for it. So it requires the image that we're going to run for these models for, an output directory. And then this directory will be where the masks are saved, similar to what we had with the initial data set. We will save them in a separate data set folder so that we can pull them easily from there. The rest of the things are kind of trivial. So this syntax, I think I will clean it up a little bit more. We'll have like default basically models here probably that you don't need to get this build models separately in. So I think I went faster. So I basically the first argument is the image that we're gonna segment. The second one is the output directory where the mask will go. The third one is the grounding DINO model we're going to use to run this image, segment this image, and the fourth one is the segment anything predictor that we've created as a result of the build models. And there's one last one, probably the most important, that would be the segmentation classes. And then you can just go classes, seg classes, or you can just say seg classes, right? And that one we've defined earlier. If you guys remember, those are just the, what is it? Facade, roof, door, and windows, or windows and doors, right? Okay, so the only issue here is we haven't really defined these variables. So what I can do is I can then go and get basically the images, right? So I'll call this IM files, right? And then it would just be os.list there. That's just a command to basically list everything in a directory. So what we're going to do is we're going to get into the directory that we've got these files in. And I will call that IM directory equal to additional underscore images. And I'll include that / in there too. And we'll just pass this in to automatically get the names of the images. Okay. What else do we need here? I guess I could do one more thing here. The run on one image requires the full path of the images. So what we can also do is, I'll call it IAMs, and I'll create a list comprehension where you have the names of each file. So for F or file in IAM files, I will do IAM dir plus IAM files. What this will do is basically prepend the image directory in front of the file name so that we can pass those files straight into the run on one image method. I think that's good. I have an issue here, right? Let's see. This should be IAM. Okay, and then IAM files, I have a typo. Okay, so this will just create a list. Actually, let me run this right here just to show you what it does. So that's just the name of the directory. I'll show you what IAM files gives us. Print IAM files. Okay, I didn't run this cell. That's why it's not able to see it. Okay, so these are just the images that are in the additional images folder that we've just downloaded. And what this will do is it will basically make them full paths. So I can do, it's just a convenience in passing the images in. The IAMs. Yep, so nothing fancy. Okay. Okay. All right. What I can do is I can just run grounding DINO for one image here, but I can also just run this whole thing through a for loop, and it will give me a bunch of masks and so forth. So what I can do is let's write the output for this. So the first output will be the pixel mask or just the mask. But this will be not saved. It will be just a file that someone can take and use. And the other one will be the path of the mask. So saved mask, I'll call it. And this will be just a file like similar to what we had earlier. Okay. So I will take these out. All right. Okay, so I will do now for IAM and IAMs, and I will put IAMs here. Actually, IAM here for individual image. And we can get fancy and we can just put like from TQDM, import TQDM. This is just to give us like a sort of a loop counter, TQDM. And then I guess I'm missing one last thing here, the directory where the masks are going to go. And that one I will, let's see what we want to call this. Let's call it segmented images. Okay. All right, so we have everything. I'm going to click the run button, and then I will quickly sort of, pause this and then add another basically command just for the overlaid image. I just want to make sure it's running okay now. Okay, so it's getting the grounding DINO and SAM predictor models. And if you see a message that says it's going to run on CPU, something's probably off with your configuration, as long as you have a graphics card. You should probably fix that, because otherwise you're looking at pretty long run times. So right now everything seems to be okay. This is running on CUDA. It's downloading all the components necessary for running this model. Okay, we still haven't hit the loop yet. So you're not really seeing the model runtime just yet. This is just still downloading and setting up stuff. Okay, I think I missed something here. Let's see. Additional images, building. Okay, it looks like I made a mistake here. Building segmentation, validation, images 82. Okay, I didn't pass in the right names here. Let's see. Yeah, I don't know how I missed that. Okay. Let's see. So this is fine, and that's okay. Okay, this is my issue, I think. Files. Okay, and that's the image directory. Okay, then there's something wrong with my list comprehension. For IM file and IM files. Not sure why it's doing that. Let's see. Oof, okay, I now see the issue. This is a list and I messed up my list here. Yeah, okay. Just see it. Let's see. Okay, so that's okay. Yep, that's it. You got it. Thank you so much. There you go. Thank you, Rachel. And I'll hit run again. This is the downside of coding on the fly. Occasionally, it's these little things. Okay. So the model installation shouldn't take as long. It should jump straight into basically running the code now. It's still downloading a few additional things that it needs for the first step. So even though we entered the TQDM loop, it's gonna take maybe a minute to set this up. But once things are installed, it should be pretty good to go. There we go. Okay. I don't know if you're seeing this, but it says it's gonna take a while. It shouldn't take that long. All right, so it will just be a few minutes. It won't be tens of minutes. But what it's doing basically is, and let me stop it right here, because I want to, I don't want to run this loop multiple times. What I want to do is also I want to add a command for getting the overlaid images so that we can take a look at what these images look like. So for that, what I'm going to do is I'm going to type create overlaid image, and then all it requires is the image path, the path of the output, the mask that was outputted, and it will also require. Typically, you would just go number of classes. In this case, it's 5. Let's see. Am I missing anything else here? Actually, you don't even need the number of classes here, because it will detect it from basically from the imagery. But you would need one more thing, and that will be output directory. I'll call it overlaid images. Overlaid images. So this is where we're going to save images that are overlaid with their masks, just so that we can take a look at them and see, do a visual quality control. Okay, I'll hit run again, and this will be the last time we're playing with the cell. And out will be the output of this step will be the images that are segmented using ground seam, which is a combination of grounding, DINO, and segment anything. So one thing that's really key here is we'll take a look at these images, and I think we won't have a chance to retrain. So please do it on your own, and if you run into issues, please let me know. Okay, I think. Let's see. I think I messed up something here. The IM will be the path. And this will be, I messed up this one. This should be the mask. And that should be that. Okay. All right. One last time. Sorry, guys. Kind of running out of battery, I think. So I will correct myself here. The IM entered will be the image path. Mask entered will be the outcome of run on one image, the pixel mask. And the output directory overlaid is the directory where we're gonna push these stuff. And looks like we ran out of CUDA memory, which means our graphics card doesn't have enough memory on it to be able to run this. That just has to do with me repeatedly hitting this run button. I'll do a, let's see. I'll try and disconnect and redo it just so that I can show you guys that it runs okay. It will take a few seconds. I won't need to download all the data here. Hit this one, and hit this one. This will take just a minute. But while it's doing its thing, I want to show you what the images look like. Just I ran this beforehand, and I just to be able to show you. And I will pull those right now and show you what they look like. Overlaid images. Okay, here we go. Okay, here we go. All right, so I will share my screen again. This time I will show you these images. Okay. The mask colors are slightly different here. The yellow is the facade. Blue is the windows. Can't remember what the doors are, and red is supposed to be a roof. So there's a misdetection here, but there's a lot of really good detections as well. So I'm just going to keep scrolling through these images, make them full screen. Zoom in some. Oh, can't. Okay. Or just keep it like this. So, I mean, fantastic predictions here, but you see what happened here? The roof was the entire top floor of the home was detected as the roof. So the point, and Fei emphasized on this too, these models are fantastic, but at the same time, they will spit out incorrect data occasionally. When they do, if it's critical for your model to really perform the task you're interested in well, it might be a good idea to, take only the data that's good with these models and then train something like we did initially at the beginning of this demo. Okay, so my point is you'll get a lot of good predictions such as this one, but then a failed, door detection. What I would recommend you do is you take these and basically manually go through them, only taking the ones that are really good predictions. Like it seems like it's a bit of a struggle for this model to figure out the door. So maybe for your initial training, you you clear out the doors and lump these classes into windows and doors or just openings, right? Here's another issue where with the roof, it's misclassifying it, but then it's doing a lot of great classifications too, right? And remember, zero shot. There's no training involved with this, right? So this is what you're going to get out of this model with grounded SAM. A lot of fantastic predictions, some issues, right? So what I would have done if we had a little bit more time is take these images, hand pick a few, push them into my training data set and keep training this model. So by distilling the data from zero shot, you can expand your data set significantly in a matter of minutes. But if you were to use this zero shot for this specific problem, and I'm not saying, these kinds of discrepancies exist for all sorts of other problems. For this specific problem, if you were to push all the data, that comes out of the zero shot model, you will likely end up with a model that will have a consistent misclassification such as this one, that it predicts the whole, top floor of a two-floor building as a roof. So these are some of the things that I wanted to sort of highlight. But let me show you that the code ran okay, and I think we're going to wrap it up because I don't want to go over time. I'm sure everyone's got other commitments. So I can't see where I get it. Let's see. I guess this one. Let's see what issue I run into this time. Oh, okay. Yep, that's a quick one. Right, let me get these images and then just show you that it runs okay. Import G down. Zip and run. Oh, we'll hit run again. Okay, some of the packages that I imported earlier are not here. There we go. Okay, this should take maybe just maybe 20 seconds or so. So the downside of skipping a bunch of cells. There we go. About everything, I think so. All right, we're finally running, it looks like. Yep, okay. And like I said, it shouldn't really take that long. And what will come out of this is basically the images that I showed you. So if you followed along and copied all the links and etc., you'll be able to create the images that we've created. The most important thing is zero-shot models are magical, but they're not bulletproof. So you need to make sure that you understand their deficiencies for your application and use them accordingly. That's pretty much all I have for this demonstration. I just wanted to thank you all for joining us today. Hopefully you've learned at least a few things about vision language models. The main thing that we're going to do tomorrow is we're going to basically go over the inventory generation and damage detection capabilities of BRAILS. There's going to be, basically just some really practical ways of utilizing BRAILS without really getting into the image recognition, the details of image recognition. So if you're interested in, creating building inventories or transportation inventories for regional level studies, tomorrow will be your day for sure. And if you're interested in, automatically getting damage detections, building damage detections from reconnaissance data, you're going to enjoy, tomorrow's session quite a bit too. And then we'll show you a few things about, how to manipulate, image data and so forth, or retrain some of the existing models in BRAILS. So it's going to be a fun day. We won't take up the 3 hours, the full 3 hours likely tomorrow. And we'll likely not go over time because it's a Friday, right? That's all I got for today. Thank you all so much for coming, and look forward to see you tomorrow. Thank you all, and look forward to see you tomorrow.